Okay, so hello everyone. It's my great pleasure to be here today. My name is Georgios Valogiannis, and I'm a new Schmidt AI and Science Fellow at the University of Chicago. Previously, I was a postdoc at Harvard. So I would like to take these few minutes to advertise our latest work, which is entitled, as you may see, Precise Cosmological Constraints from BOSS Galaxy Clustering using the Wavelet Scattering Transform. So, as you maybe heard previously in this conference, the Wavelet Scattering Transform is a novel summary statistic that tries to serve as kind of an ideal, more interpretable middle ground between traditional clustering estimators and convolutional neural networks by essentially subjecting an input physical field to a series of successive convolutions with a family of localized wavelets that spans a set of given scales and orientations. And by doing so, it essentially manages to capture the non-Gaussian information that is encoded in a physical field. In our case, it will be a cosmological density field or a galaxy density field. And in a series of subsequent works that culminated to this latest paper that we put out on the archive about a month ago, in collaboration with my former PI at Harvard, Conrad Dvorkin, and Sandy Yuan, who's a postdoc at Stanford, we performed the very first application of this estimator to survey data of any kind, to my knowledge, and to, in particular, spectroscopic data by the BOSS survey. You just heard about BOSS, the BOSS CMASS DR12 dataset. And we constructed an emulator for the cosmological dependence of this estimator using a neural net and trained from the state-of-the-art suite of the Abacus Summit simulations, Galaxy MOX. And we performed a likelihood analysis of the BOSS data. So our highlight of the results is that a joint analysis using both this WST estimator and combined with the standard two-point correlation function analysis of the multiples of galaxies produces a substantial improvement on the 1 sigma errors obtained on the lambda CDM cosmological parameters by a factor of 2 all the way to 6 times tighter compared to what one would get by just using the standard two-point function only analysis. And if you want to see our results for the growth rate, F sigma 8, which is usually quoted in RSD studies, you can see them here in blue, alongside some subsample of other past analysis of BOSS, where you can see that, first of all, we're able to obtain a very competitive constraint on this quantity, which also happens to be within 1 sigma agreement with the Planck result, here demonstrated by this black shaded line. So having said all of that, I'm very excited about all this, about this result. I believe it demonstrates the great promise that is held in the use of this estimator in the context of cosmological parameter inference and precision cosmology. And I'm currently leading the effort to constrain cosmological parameters from upcoming DESI observations, states for spectroscopic data using this WST. So having said all this, thank you all for listening, and happy to take any questions either over coffee or via Slack. Thank you very much.